Thank you very much. It's a great pleasure for me to be here, and I thank Arkady for inviting me. Thank you. So, I hope I'll be able to explain what it is that I'm doing and what is the connection to computer science, etc. Let me start, if this works. Let me start with the problem. So we jump right into the problem. We can today be able to continuously monitor a lot of organs in our body. We can monitor them, we can understand what's going on. We are able to detect problems at a very early stage. And the heart or diabetes are just one example of that, all right? Unfortunately, we don't do that with the brain. Our most important organ, our most complicated organ, the organ that really makes all the changes and all the real decisions for our body, okay? So that's what I want to do. I want to be able to monitor the brain in the same way that we are able to monitor, say, diabetes, okay? Unfortunately, diabetes is a much simpler problem. The brain is much more complex, so obviously this is going to be a little difficult. We'll see how we can get there. How big is the problem? The problem is very big, okay? Numbers are huge. The point is, nowadays people talk about the fact that every sixth child suffers from some kind of developmental disorder during the course of their life. Okay? If you take dysgraphia, dyscalculia, attention deficit, etc., altogether it's 1 out of 6 kids. Okay? And if we can monitor those brains and we can devise tools, computerized tools, to help them, obviously we can really improve development at a very early stage of the kids, at a very early stage of the development of the problem. This slide is really to show that migraine is one of the biggest problems. We'll concentrate on migraine later on in the talk. It gives you an idea about the other problems that one deals with when trying to monitor the brain. So this is time to introduce myself. Yes, I'm a professor in computer science and neuroscience at Tel Aviv University. Basic training is in math, pure math and applied math. So I have no training in computer science. I'm doing signal processing, which is based on math. I'll mention about it a little later. And I'm also into entrepreneurship. These are my more informal colleagues, and I'm very happy to introduce them. The dolphin, which is the most amazing sonar animal in the world, from which I learned a lot. The sonar bat, which is the companion for the dolphin, so this is in the water, this is in the air, this is under the ground. The mole rat is an amazing species for studying brain development, and the elephants we'll get to a little later. Each one of these animals has a capability, has a brain capability that's far beyond of what we can do today. Okay? Far beyond the machines that we can generate today. If we are comparing the ultrasound to the dolphin's ultrasound, the dolphin is about 100 times more accurate. If we had an ultrasound with the accuracy of the dolphin, we could detect early problems in fetal development, early problems connected to brain cancer, and any other cancer. We could really remove the need for CT, MRI, PET, and whatnot, if we could do what the dolphin can do. So that's an issue for engineers to be resolved. How does the dolphin do that? Okay. The next few slides are going to be a little bit more technical. Just a few slides. Bear with me if you're not familiar with signal processing. Don't worry. I'm going to take off without it. So this is a very important criteria. This is Heisenberg, who was the student of Niels Bohr. Heisenberg became the head of the Nazi atomic program. Niels Bohr went to the American atomic program. So their ways definitely split, but it is believed that because of Heisenberg, the Jews in Denmark were saved. So maybe he did something useful after all. His criterion is that you cannot localize in time and in space above a certain factor, okay? So you cannot localize infinitely well without going into an infinite bandwidth of the signal that you send, okay? And then when we look at the dolphin, we can record the signal that the dolphin is sending, and it turns out that the dolphin localizes better than this principle. Now, I'm not saying that we are breaking physics, because there's an assumption there. The assumption is that this is done with a single expert, or with a single, what's called cross-correlation in this case. And it turns out that the dolphin or the bat are breaking the signal into multiple parts, and these multiple parts, when fused together in a smart way, actually get better result than what a single expert can do. So while the theory has been sealed, in 1953, turns out that the dolphin is still doing much better than what we have devised in the last 60 years in that area. I'm going to get into a little bit of the details of what I just explained so that this is a bit more clear. Okay, I see that I have a little problem here. I'm sorry about that. But this is the sonar bat emitting signal and being emitted to a target and received. And what happens is the bat is breaking the signal in the ear into multiple bands. Those multiple overlapping bands, this is the chirp that the bat is sending. These multiple overlapping bands, when applied a single expert or a single cross-correlation to each band separately, the result is worse than the result that would have been achieved when applied to the whole signal. This is a theory, this is Woodward's theory from 1952. But it turns out that if one applies one expert to each one of these bands separately, okay, one can get a better result. To see how this works, let's look at just 2 or 3 more slides, technical slides. This is the classical cross-correlation function for those of you who are familiar with. At the top is what's called a coherent receiver, and at the bottom it's a semi-coherent receiver. So the level of noise is so big that we are crossing the detection of the peak here, and we may be crossing to side lobes, what's called side lobes of the cross-correlation function. So coherent receiver is where we want to be. Semi-coherent receiver is where we end up when the level of noise is too high. And what one can see here with the different patterns here, they are related to different parameters of the band that is being sent. When the bandwidth is higher, we are in the more narrow region of the signal, and our accuracy is actually higher. Unfortunately, when the same band is higher, the side lobes become higher, and so our possibility to jump from the single peak to the side lobes, namely lose accuracy quite a bit, is becoming higher. Apparently, the sonar bat understood that, and instead of doing what is classically still being done in sonar, this graph represents signal-to-noise ratio versus the accuracy. We see that when the signal-to-noise ratio is very high, namely the signal is of high quality, there's little noise, the accuracy is very good, okay, or the root mean squared error is very low. Then at some point we break from what's called the coherent receiver to the semi-coherent receiver. And from here, of course, the accuracy is much worse. Look what the sonar bat can do. The sonar bat, this is a model. This is a model that we devised based on our understanding of what the sonar bat is doing. The sonar bat, by looking at different frequencies separately, is able to really choose, and we have suggested a mechanism for this choice, is able to choose the right bandwidth based on the level of signal to noise. The band has a way to estimate the noise. Actually, the same thing really gives you a level of the noise very easily, and can switch between these experts in order to actually stay in the coherent receiver for much longer and really get much better accuracy. You know, there were thousands of papers written after Woodward's seminal work in '52. This came out of a sonar bat. So I guess the bat did not read those papers. What is really happening here is that the animal is devising a very sophisticated data representation. Many of you are doing machine learning, I believe, yes? So you're familiar with mixture of experts, okay? What Jeff Hinton calls mixture of idiots. The idea is that you take experts and you make them not as good compared to one another, definitely not as good as the optimal expert. And then if you mix them, you get much, much better result. And apparently this is exactly what is being done here. And once you understand that this is a concept, you can really think of totally innovative ways to really create those experts. And each expert by itself really doesn't have to be so good. We'll see that in a second when we go back to analyzing the brain. So another demonstration of this is not by splitting the signal into different bands, but by actually doing something far more sophisticated. We are exploring the same signal with a bunch of what's called cross-correlation, or signals that are similar to the signal that is being sent with a changing phase only. This change of phase actually invokes very sophisticated theory in statistics, because this is now an unbiased estimator. It has a tendency to have an error bigger in one side versus an error bigger on the other side. As you can see, like the green here, the error is smaller. Here the error would be larger. Apparently this little trick, when fusing now those experts together, again gives you much better result. Okay? This was modeled after the mole rat, which is using infrasound to explore the underground around him. So the key of what I learned from studying those sophisticated animals is that one has to create a very sophisticated representation. The complex representation makes the calculations very simple. That is really the key. Complex representation, which is what takes time to learn, makes the calculation later very, very simple. So when we are born, in the first year or two, we listen to speech, usually of very few people, like our parents, and we are creating those tools, we are creating those signal processing features in our brain that enable us to understand speech. It takes us about a year to create those. Once we create them, you see that the baby picks up and starts learning new words, etc., very, very quickly. And if we don't learn them in the first several years of our life, we cannot learn them later. Okay, so there's a critical period around the age of 7, between 7 to 13. If we were not exposed to language at that time, we wouldn't be able to create those features. So this is a formidable task in our brain. Let's try to take that into the other direction, into really brain analysis. So now I'm looking at this brain as emitting a very sophisticated signal, a very complex signal, and I want to analyze that that signal, okay? So we'll try to use brain-inspired and advanced signal processing for that purpose. Let's look at the problem. The problem has been known for over 100 years, and the really seminal work in this field has been done, embarrassingly, about 90 years ago. This guy, Hans Berger, with prehistorical signal processing technology, was able to demonstrate that the brain emits several signals, several bands that are typical and are related to some of its activity. So he termed those bands alpha, beta, gamma was discovered a little later. And basically, since that time, very little has changed. Thousands of papers were written, but in 2015, still papers are published and are using the same language that he used 90 years ago. So you can read a paper saying that alpha is going up and beta is going down on one side or another side of cortex, and this is really what he devised. Obviously, there's a way to do better, and signal processing, the revolution in signal processing started in the 90s, so we are now 20 years into signal processing, and by that time we understand really what one can do with it, and this is the niche that I'm getting into. Advanced signal processing to analyze the brain. So this is still 2015, this is where we want to go to, okay? In order to make this continuous, in order to make this mobile, obviously we cannot stay with this, okay? And I'm even more ambitious. I want to use something very, very small like this, but get information even more than one can get from here. Well, why is it complicated? So some technical issues. Part of them is actually true. So it is said that the signal decays as it is being emitted to the skull, and we are recording on the skull. It is true that the signal decays, but it doesn't decay so badly so that it cannot be read. But still, the belief is that one can really only read with a single electrode an area that is very close to that electrode. That is absolutely wrong, but people still believe that. Something else, and this is actually helpful for us, so neurons in regions on different parts of cortex actually emit a signal that is kind of colored by the location in the cortex, by the type of network that is being activated, the type of synapses that are there, the length of the synapses, the type of neurons, etc. So different regions really produce a certain color to the energy that they emit, and this is something that we can really read and we can really rely on, as we'll see in a second. The future technology that will make each one of you be able to carry a brain monitor without anyone noticing it is this very thin electronics that is being developed for the US Army for the last several years. This is really very thin electronics that can be stuck as a tattoo, a totally see-through tattoo. And what it can read is really amazing. It can read electricity, so it will be ECG if it is put on the chest. It can read EEG if it's put on the forehead. It can read EMG, which is the muscle electrical activity, if put on the muscles. It has temperature, strain gauge, LEDs, so it can transmit and read pulse oximetry, etc. And what I'm developing is really for this kind of technology that will become available commercially in the next few years. Once we have that, we need to do some signal processing. So I'm not going to go into the signal processing, but I'm going to describe something that each one of you is familiar with. You can sit in a concert hall, very far from the orchestra, close two eyes, close one ear, and with the one ear, you can really listen to the whole orchestra and decompose the different instruments in your brain. So you can easily distinguish between violin and a trumpet, although they reside on the same frequency band. Why? Because we say that those instruments have a color or timbre, okay? So we would say that a trumpet is metallic and a violin is warm, And those with much better musical ear, those that usually were exposed to music at a much earlier age, can distinguish between a Stradivarius violin and another violin, etc. Okay? Signal processing, this is very difficult. We don't know how to do it. However, each one of us can do it. So obviously we believe that there is a solution. This is really what I'm trying to do with the EEG signal. As I said, the EEG regions, the different functional regions which emit their signal, are colored by the topology and by the location of where the signal is being emitted, and this is really what I'm trying to do with the brain. I'm not the only one. Elephants can do it as well. Okay? So these elephants which communicate, by the way, the bigger the animal, the more sophisticated it is. It's just more difficult to put them in the lab, so we don't study them so well. Okay, it's easier to put a dolphin. The sonar of a humpback whale is even much more sophisticated. Okay, so these animals, which live in the desert, an area where there's a lot of fires, communicate with one another by clapping their feet on the ground. So one elephant can go in the forest and see fire, and an elephant 5 kilometers away would start running away. But more importantly, they have those seismic sensors in their feet, and they can detect earthquakes, among other things. So, question is, can we do that? It turns out that the most sophisticated signal processing technique was devised for seismic data analysis. So seismic data analysis is considered a very difficult problem. Now, about 2 years ago, when I was working on my technology for EEG, we had this earthquake in Fukushima. And being an optimistic, I said, why not try it on seismic data? So this is how it looks on seismic data. Here at the top is the seismic data before the event, and here's the earthquake, a jump, and then some aftershocks. When I pass it through my signals and I find a certain anomaly, or you would say a single musical instrument that is playing in this complicated signal, okay, it turns out that I see an anomaly between 14 to 3 hours before the event. Okay. In Fukushima and in Japan, for some reason, this anomaly goes down just before the event, but in areas like California, this anomaly doesn't go down. So there's a different anomaly there, which stays much longer. Where does this come from? From the transfer function that is a function of the path of the signal from inside the Earth to the outside. As you can see, it's a very similar problem to reading EEG. I mean, the head is slightly bigger. Okay, the sensors are not EEG sensors, but seismic sensors. But we are looking at an event that is happening inside, and we are trying to read it outside. So it's very, very similar. Same anomaly occurs in the aftershocks of that event. Here I show that I can really tweak a function, and I can emphasize that anomaly as much as I want. So there's regularization going on here. This is, by the way, a perfect project for Yandex data to really put all this on the cloud and analyze all the stations in the world. What the elephant tells us is that really I care only about one station as opposed to the huge sophisticated network of seismic sensors that is put in the world, and people are looking for connections between them. Just like people are recording EEG with a lot of sensors, the elephant can sense the earthquake next to him, and is actually trained to go to the mountains because I guess for some reason they know that an earthquake can be coupled with a tsunami, and it's better to go up. Here it's in Fukushima, here it's in another earthquake in Toku, slightly different anomaly. And this has now become a project where we study different regions, see where it is that we can predict, where we cannot predict, based on this kind of signal processing technique. So let's go back to the brain, and now we are starting really to talk about the brain in terms of this new brain activity features that I've devised. The tools are large data set of EEG signals. As you know from machine learning, your performance can not be better than the data that you have. So the idea is to really handpick the data or create the data very well. The mathematical technique is harmonic analysis, basically orthogonal decompositions, but coupled with machine learning. So harmonic analysis is not familiar with noise. When we introduce noise, and this is obviously what we have, we need robust statistics and big data analysis. Okay? Altogether can give us some features, and let's look at some features. Okay? So we're going to look at some pictures like this one, where the x-axis is time and the y-axis is features. So we have 121 features here, okay, that are collected from a single EEG lead, which is the difference between two electrodes. Single EEG lead, single microphone, single seismic sensor can give us this 121 features. Each feature by itself is not very smart, just like when we talked about the bats. However, the combination of those features, if put together, can really tell us a lot about what's happening in the brain. But as we'll see from these pictures, we can really start seeing things very quickly from them. So this, for you, is a simple kind of the first part of a lie detector, where a person is choosing a card among 5 cards, and then is being asked 5 questions. Is this the card? He has to say no. Is this the card? He has to say no. In one of the answers, obviously the person is lying, and this is what we want to find out. Where do you think the person is lying here? Here are the answers. 1, 2, 3, 4, 5. Any, Konstantin, what do you say? Where is he lying?
Those 3 columns.
He lies only once. Only one time there's the wrong.
Well, the number 4 looks different from 2 and 3.
Okay, so here's what really happens. Here there's anticipation for lying, leading to very long and very intense activity. So the red lines indicate stronger activity of that region or functional network. As I said, those different features were found with a mathematical method on the signal. So they were kind of automatically found with a lot of constraints to really find them, okay? And now what happens is, the longer the activity is, the more functional brain regions are participating, the stronger the color or more red, meaning that that specific network is more active, okay? Kind of like functional MRI, which measures the saturation of blood or the oxygenated blood. And this is here anticipation. This is really the indication of lying. So he's really lying here, and look what happens after that. Once he lied, he already knows that he lied, so the next 2 questions are trivial, and as you can see, there's really no brain activity when he's answering for the next 2 questions, okay? And when looking at the actual questionnaire of the person, this is asking people, you know, during a job interview. Maybe, Akadi, you want to use it here. So they're being asked a lot of questions. Did you take drugs? Do you have money in the bank? Did you whatever? Okay. We see here three areas where there's stress, 1, 2, and 3, where there's stress compared to the other answers where maybe this required a lot of mental activity to answer, but did not produce that much stress. So this is now being connected with a lie detector, which measures, of course, external things to the brain, you know, like GSR, galvanic skin response, sweat, stress, etc. And this is kind of orthogonal to what this is done. But I really used it to introduce my representation. So a lot of features, we will see that they are nicely ordered, again, mathematical constraints to order them. And we will see a lot of this kind of vertical signals. This is an example of a pilot that's an experienced pilot who is flying a flight simulator, but a serious flight simulator, not a game, a serious flight simulator. And you see again the activity in this kind of elongated vertical lines. So we see that here there's much more activity. It's very easy now to see. Okay, this is where he's performing the more difficult tasks in the flight. This is when he's kind of flying towards the area. And what's interesting is from here, he's actually giving the joystick to the other pilot. So you see that his brain activity, although the kind of simulator is shaking exactly the same, but now it's the other pilot that's flying, and we see that the brain activity of the first pilot is much reduced. However, if you look at the bottom line, you remember that indicated stress before, we kind of see that he's more stressed when the second pilot is flying the plane. He's less stressed when he's flying the plane. So this is a nice separation between the ability to measure stress and other emotions, which we'll see soon, and the ability to look at the cognitive load of that pilot. Okay? And you can imagine that this can be very, very useful for monitoring pilots and seeing if they are, their level of fatigue, their level of attention, etc. Same thing exactly happens when you do a cognitive test to an elderly person for looking at some dementia. The person is being asked questions, and these lines indicate the answer of the person. As we'll see in a second, this kind of faint line in the back has to do with emotions. We can see some stress in this response as well. We can distinguish between stress and happiness. This area here actually indicates happiness. This is when the person was asked about his kids and was kind of very happy to talk about his grandchildren. So we can really see what created higher cognitive load. We can really see what did not create any load. And of course, if we want to monitor elderly people, this can be the Fitbit of monitoring the brain of elderly people. If we enlarge it, we see it in more details. The amazing thing is that there's a certain time difference between each one of these lines. That's a very strong indication that this is brain activity, cognitive brain activity. When there's no distance, this turns out to be deep sleep. We'll see that in a second. One comparison to more conventional techniques. This is on a project of analyzing the brain problems of premature babies. These are babies that were born during some stress of the mother. Sometimes the mother gets a heart attack, sometimes the delivery takes too long. And basically for a certain time, that baby did not get enough oxygen to their brain. And the big question is, if this baby is going to be a normal, healthy human being, or is actually going to be a disaster for himself, for the family, and for society. If I tell you what is the technique that doctors are using now to answer these cardinal questions, it's kind of prehistorical tools that were devised in 1926. Okay? The data that was used for FDA approval was collected in the early 70s. The approval came in mid-80s, and that data or techniques to analyze the mid-70 data were really devised way before. And this is still what is being done. So in comparison, and here I presented my features in a way that's kind of similar to this, you can see that there's much richer structure that can be seen from the same brain activity, okay? So this is recorded with the same electrode that is, the data is being recorded, and this is just the analysis, it's just the analysis, and you can see that there's much richer activity, and basically it's the richness of the activity that determines the level of brain damage. Okay? What I'm really constructing here, I'm really constructing an alphabet from the brain activity of that child, an alphabet, and then words, and analyzing grammar, just the same way you do with text. Okay? The alphabet that is being used by doctors to analyze that brain now has two letters, awake and asleep. And they're looking just at some kind of a circadian rhythm between switching between awake and asleep to determine that this is an okay brain. Very interesting problem. Let's look at some other representations. So all the data that we are seeing is coming from the same features, the exact same features, with the exact same ordering of the features, and is being analyzed on a lot of people, okay? Here is how a cognitive task looks like. The task requires, so we have one person, 2, 3, 4, 5, 6, and a short part of a 7th person, okay? The task at the beginning is to read or listen to some text, so observe some text, then some questions that have to do with memory, and then some questions that have to do with deduction or with understanding the text. What's interesting here is that this person and this person look very similar. And in fact, this person's starting to look similar as well. This is the mother and son performing the same task. This person, can you guess what happened with this person? He did not read the text. He immediately went to the questions and then read the question and then went back to the text and tried to answer that question. This happens a lot for people who don't trust their brain or don't have the patience to read the text. This person has some, well, I'm not going to go into it. But these two are different. This is somewhat similar to the other ones. So what we see here now is that not only we can look at concentration, attention in general, but we can really look at cognitive strategy when trying to solve a problem. And you can imagine that if we knew what is the cognitive strategy that someone uses and notice that someone does not use a certain strategy because he's not good at it and he's trying to compensate, that would really help us to be able to detect it. If we add, so here's the data of the 6.5 people that we saw before, and now we want to demonstrate the profound effect of meditation. So this is meditation done by two Russian teachers for meditation. You can really see the change in brain activity as is seen. This is a novice trying to do meditation. You can see that it doesn't look like that, but it also doesn't look like the teachers. So if we are talking about neural feedback or indication telling someone how to perform meditation well, this can be an amazing mirror indicating how to do it. Because a lot of people could really benefit, and now research suggests that meditation is extremely helpful for a lot of brain problems, social problems, and whatnot. A lot of research is done in Wisconsin on that for kids from age 5 and up, and just good things are being devised. When we put, not we, but NYU and Wisconsin, when they put Buddhist monks into functional MRI, and they do meditation inside the MRI, it turns out that something very similar. So a huge portion of their brain kind of shuts, and this brain region, which is very distributed, is called the default mode network, for those of you who are familiar. So basically the default mode network shuts, and there's an area that remains very, very active. That area is medial prefrontal cortex, an area that's kind of in the front, has to do with decisions, and also has to do with positive mood. And we'll see now that area coming up in the next few slides. So this is, again, the profound effect of anesthesia. Here the person is awake. This is the beginning of anesthesia. Here, pain is inflicted for the first time. This is a laparoscopic operation, so they just put some tools inside, and you can see the effect of pain. We'll see that a little later as well in other things. Here is where they induce more anesthesia, and now it's the laser knife that starts cutting. You see that this activity is being further reduced. Again, the BIS, or the tool that is being used now to monitor anesthesia, is prehistoric. Okay? Why do we need to monitor anesthesia? Because the current protocol says that one has to get amount of anesthesia proportional to their weight. For young people, this is fine. For elderly people, this is very bad. This is way beyond what they need. We'll see in a second how anesthesia of a younger person looks. And so they get too much anesthesia, they don't recover from the operation, dementia kicks, and you many times hear about a person who went for a knee operation. The knee operation was fine, but he never got back to himself. So it's extremely important to monitor anesthesia. Some other demonstrations of anesthesia. Again, this is the laser cutting. The laser is electric, so it creates a strong electric noise, and we cannot really analyze the data here. This is an anesthesia of a young person. And in a second you'll see that it looks like deep sleep, totally different than what we saw before. So let's go to sleep. These are the different stages of sleep, as we can see with our sensor. Much more sophisticated than what can be seen with the classical technique of monitoring. We see that the early sleep looks like anesthesia. Then there is the REM, or what we'll see soon, dreams, and we'll see that this looks roughly like watching a movie. And then we have this kind of snow, which is deep sleep. Again, I remind you, it's exactly the same features. So all the data you're looking at is coming from exactly the same features. If we just emphasize the early part, we can see very interesting things just there. So this is a person trying not to fall asleep. We can see this part is called hypersynchronicity, where there's a lot of activity in the brain. One can see that it's kind of a wave that goes throughout the brain. We saw the same wave also in anesthesia. We see it also in meditation, and then falling asleep. Another expansion of this in a different case is a very interesting situation where, again, this is the falling asleep, and now suddenly it's like two different orchestras are starting to play in the brain. Okay? All can be seen with a single electrode. This is what I call a sleep symphony. Okay, this is dreams. This is the dream part, and you see an amazing activity of the brain. Okay? To connect that, we look at what happens when we see a movie, and we'll see that this is really similar to what happens when we see a movie. We'll connect that to emotions, and the idea here is to really be able to tell whether the person had a very happy dream, or a bad dream. Why do we need to do that? Because people who suffer from trauma, post-traumatic people, their dreams totally change, and this is one way to detect those kind of changes in their brain. Again, dementia, the dream or the sleep patterns totally change, and this is again a very good way to determine what happened. And people get excited about that because if you combine falling asleep and watching a movie, you actually get something very interesting. So this is a person watching a movie, and what you see here is the part of watching the movie. This snow that you see here is when that person is falling asleep while watching the movie. In fact, not really falling asleep, because if you look in the back, you see that this kind of line of thought is still there, and you also see it here, kind of starting from here and going here, and now watching the movie again. Okay? So we can really determine engagement here with the movie, or when the person is much less engaged. I kind of do this experiment with my students. So when I see a student that is kind of partially falling asleep, I immediately ask them a question just to see if they really remember what happened in the last 5 minutes, and they actually remember. So it's exactly like this. They are still engaged, but for example, I would not like them to fly my plane at this brain state, okay? So neuromarketing is very excited about that, because this can really tell you about engagement with the program, with the advertisements as well. But again, as I said, pilots and other are excited about that as well. So this is how a movie looks like. Again, the same feature. This is one movie, this is second movie, and this is the third movie. The first movie is rough, violent. The second movie starts very happy and ends very sad. The third movie starts sad and has a very happy end. And you can see the arrows point to the happy part in the movie, and you see the same activity that we saw in the meditation, in anesthesia, and based on functional MRI, we can conclude that it has to do with medial prefrontal cortex, an area that is important for feeling happy. By the way, feeling happy about the others, not feeling happy about myself, which is in a different region. Okay, the kind of feeling happy when you see a happy movie. Okay, so this is very interesting, because the literature tells you that EEG cannot read emotions. Why? Because the emotional part, the amygdala, is kind of buried, is a very small part, and is buried inside the brain. And it is thought that EEG electrodes cannot really reach that part. In a study that I do on post-traumatic people, when we put them into functional MRI with EEG on top of them, so it's a very sophisticated technology, EEG going into this strong magnetic field of functional MRI, we can actually demonstrate that we can read the amygdala. So apparently what is believed is not correct. This has turned into a neuromarketing study with CBS, and the bottom line of the study is that we can take an hour of program and provide second-by-second response on a large group of people, being able to tell when they're engaged and when they are not engaged with the program or with the advertisement. These are the advertisement parts in this program, and what one can see is something that they are actually trying to do, which is increase kind of the engagement just before the advertisement starts, so that people will not switch to a different channel because they really want to see the rest. During the advertisements themselves, they sometimes do a promo of the next episode in order again to increase engagement. Turns out that you see this here very, very easily. Now, neuromarketing is a huge business, and the ability to do it remotely, wirelessly, in a mobile fashion with just 2 electrodes is very, very appealing. What we can learn from this is not just engagement versus non-engagement. We can also really analyze the specific brain state that the group has been in that time. And we see that here, for example, the engagement has to do with one brain state. Here the engagement has to do with a different brain state. And here the engagement has to do with another brain state. So we can really get into the emotions of the collective group of people with this technique. Consumer market, in addition to this, now we are looking at augmented reality, virtual reality, goggles of all sorts. Turns out that it's very easy to put the electrodes in the front, and now you suddenly have a person that is playing a very strong game, and one can read their emotions and their brain activity throughout the game. Of course, this can also be part of the game, and he can influence by his thoughts, his game, or someone else's game. Very interesting. So the current system for neuromarketing is reading the brain. This is a proof of concept type of sensor, very simple. Wireless goes to the phone, goes to the cloud. This can be replaced by other clouds. And then being able to read the signal anywhere, from the cloud. This can be read anywhere. A lot of data analysis here. And the real goal is to really be the one technology that will put brain activity onto the cloud. So not just have all the text of the world on the cloud, but really have all the brain activity, or as much as possible brain activity on the cloud. Because when collecting continuous brain activity from a lot of people, one can learn a lot about brain, and one can advance brain research tremendously. A lot of it did not advance just because we did not collect data. See what happened when we started collecting continuous data of diabetes. Now, managing diabetes has become very simple. We provide insulin at the right time, and these people don't suffer anymore. Just a generation ago, people were losing their eyesight, losing limbs, etc., from the same diabetes. So now imagine that you're taking your brain medication, whether it would be for migraine, whether it would be for epilepsy, whether it would be for mood, without knowing what your brain state is. And this is really what happens nowadays, and this is what we want to change. I didn't mention this can be done on dogs as well. That's a project that we have. Unfortunately, this is very dark. This is a beautiful Malinois dog. I fell in love with this dog, smarter than anyone I know. The sensor is right here. This dog is a sniffing dog, and the idea is to separate the dog from the operator so as to really become a bionic dog that one can detect when the dog detects what it needs to detect. And you may know that nowadays dogs can sniff or detect cancer in odors, and that's a huge, huge market. And the idea is, of course, to make those dogs more independent and to quantify, to really have a very quantified result of the brain activity of the dog. But what we really want to do, other than neuromarketing and all these tools, we really want to impact brain and improve the brain, not just read the brain, not just monitor the brain, but really improve the brain. There's very strong indications that there are ways to train the brain to become much, much better. There's this recent work about gaming, how they can improve the brain. And there is this slide by Adam Gazzaley indicating how different stimulations can really improve the brain. So in order to improve the brain, we really need to have a very good sense of what is going on in the brain, and this is essential. Currently done in the clinic, a person goes, we put a lot of those sensors, is sitting in front of a screen and is performing this neural feedback. So the person has to get up, go to the clinic, have a technician, put the stuff on them, and then he cannot do anything else, and he's doing neural feedback. Obviously, that's not what we want to do in the 21st century. We want the sensor to be mobile and to be on the person, wherever that person is, so that neural feedback can be done at all times. During driving, during this lecture, anytime. And the feedback can be the vibration of the phone in your pocket, or or musical feedback, anything that you can think of. This is really where we want to take this. This, of course, with a technician and this equipment, is very expensive. It can become much, much cheaper. Why migraine? I mentioned migraine before. One of the biggest problems, apparently a lot suffer from it. Okay, this indicates that this is a very good business opportunity. Research opportunity, but also business opportunity. When you have 3 U's, okay, so it's underestimated, under-recognized, and under-treated, that means that this is an area to go into. And this part now, to me, is the most fascinating, and you'll see now with the same features, something that we haven't seen before, okay? So this is abnormal brain activity. This is abnormal brain activity of an epileptic person feeling a migraine, okay? Why is it abnormal? Because suddenly we have features that remain active all the time, independently of the activity of the brain. Before, we only have seen vertical lines, and now suddenly we are seeing these horizontal lines that start in one place and end in another place, okay? And they represent abnormal brain activity. To me, this is also kind of a miracle, because I devised those features on normal people, and now it turns out that when there is abnormal brain activity of the kind that happens in either migraine or epilepsy, it turns out that a single feature, this is a single feature, becomes active. Of course, there are other features that may become active in other areas in the brain, but it's not scattered among features. Somehow those features really capture a functional region, that all this functional region becomes active when there is abnormal brain activity. And now you can see that you can tell where it starts, you can tell where it stops, you can see that it may stop very abruptly and then be gone. So suddenly you can peek into the brain in a way that has not been possible before. You can peek into the abnormal brain as well. And I'll show you some more examples just to persuade you. So again, don't ignore this. These are some kind of expert that I run on the data, so this have some indications. The point is, you can have a region without abnormal brain activity. Suddenly the abnormal brain activity starts. It can end. And maybe most exciting, if you remember this region, this is what we called the happy region, or medial prefrontal cortex. Here we have an amazing example where there's abnormal brain activity. Suddenly this area becomes active, that happiness part of the brain, and this happiness stimulation stops the abnormal brain activity completely. So suddenly we can look into the brain with eyes that we did not have before and really see what is happening in the brain. Really quantify, just like we try to quantify in lifestyle today, you know, how my food affected me, how my sleep affected me, how exercising in the morning versus exercising in the evening, drinking coffee, not drinking coffee, how all this affects everything in my body. And suddenly we can look into abnormalities in the brain in the same way. By the way, people try to predict epilepsy, and the current state of the art is really predicting epilepsy at the level of minutes before the event. Here I'm looking at patients with that are days before the event, and I can see this abnormality. I can see where it starts, where it stops. Sometimes it develops into an epileptic seizure. So this is how an epileptic seizure looks like. And one can see that here, while the seizure stopped, you see this abnormality suddenly starting again. Okay, you can really look into the brain in the most detailed way. No one can do that with the current EEG technology. So you can put 264, and I'm working with patients that the current system cannot really help them. So they are being hospitalized. They do this, what's called video EEG, if you're familiar with, where you sit in front of the video screen for a week. They take off your medications. You get about 2 seizures a day, and they try to tell where the focus of the epileptic seizure is. And these people, this kind of detailed activity, by the way, this is the same person, this is normal brain activity. You see no abnormality here, and here you see the abnormalities in the different regions. Okay? So this is, to me, the most exciting part of this work. So for neural feedback, it's again the same system where this can be either a game or a musical neural feedback or any other neural feedback. I'm getting to the end of my talk. There are competitors, there are people that try to read the brain. These are all using 1 or 2 electrodes, and none of them is trying to do this kind of sophisticated medical graded reading into the brain. These are the most sophisticated multi-electrode methods, and other than these 2, which are using slightly more advanced signal processing techniques, the others are using very conventional 1926 model T of EEG activity. T is for the Ford Model T. So to summarize what we have, by being able to read the brain in a very detailed way, or interpret the brain in a very detailed way, one can apply it to lifestyle, of course, diagnostics and very early detection of problems developing, neurofeedback, which is really the management and part of the therapeutic part of the idea, brain monitoring for various tasks. For example, I mentioned the pilots. I could also mention students. In the future, we shall be using Coursera, or students will be studying in class with a robot, namely a computer. Those kids that are very bright will go at the speed of the computer and will do very well. Those kids with attention deficit or with other problems, emotional issues, will actually get stuck because the computer will not be able to tell that they are not paying attention or that they are unable to right now concentrate on the material. So brain monitoring will be crucial. Of course, brain-computer interface, and I presented this dog, bionic dog, as an example. And all of this relies on really big data analysis on the cloud. The data is going on the cloud, is being analyzed on the cloud, and then being returned to the doctor, to the caregiver, to the person, etc. Thank you very much. Questions?
If you got a question, please raise your hand. I'll give you the microphone, then you can go ahead and ask him.
Good evening. Good evening. And it's very good conversation, but how does first part of it linked with second?
How does what?
First part of it link with second, because in first part we talked about Fourier transform that our brain does, but in second part there are
I gave
just images of
I gave 2 examples in the first part where the brain creates. Okay, let me repeat the question. The question is, how does the first part of the talk connect to the second part of the talk? So the first part of the talk basically is what I did before when I was studying the brain and tried to understand the amazing brain signal processing capabilities of the brain. One outcome of that was that you really want to create multiple experts, multiple features, each one not necessarily the best, but as a collective they can really indicate something very good. And in the first part I showed two examples of devising such features. One is a simple one done in the cochlea where you really split into frequency bands, the Mel scale, if you're familiar. The second one was actually by a more sophisticated way of analyzing the signal by this phase, different cross-correlation with different phases. But both of them, and I demonstrated in the BET that one could improve the result by expert fusion, by ensemble of experts that was sophisticated. In the second part, I created, again, a lot of features using harmonic analysis, which was slightly higher, more sophisticated than Fourier transform. But with harmonic analysis, I created a lot of features. Each one separately is not necessarily so useful and is not as good as, say, gamma or alpha if we go back to 1926. But the collection of all of them is actually very strongly indicative of some sophisticated brain activity. Okay, so that's the kind of connection.
More formally, can we imagine how brain in experiment can do Fourier transform? Because all sounds
we can
take as
very simple, very simple. Okay, I would say, okay, just kind of as an example to understand this, the sonar bat has neurons that have kind of a clock speed of 2 kilohertz, okay, because there's a refractory period for each neuron, which is about 1 millisecond. So the clock speed is really cannot go beyond 1 kilohertz. And the sonar bat can distinguish between signals, do you know at what resolution? Of less than 100 nanoseconds. Okay, so you take now stupid neurons that have a resolution, temporal resolution, it's very easy to demonstrate that. Simple neurons that have a temporal resolution on the order of milliseconds, you combine them together in a sophisticated way, and suddenly you get a collective resolution that is less than 100 nanoseconds. Very sophisticated, okay? The combination of experts is the key. But let's not continue, we can continue later, okay?
yes,
First,
Yeah, it's okay.
I would like to thank you.
Thank you.
It is really fascinating and groundbreaking.
Mm-hmm.
3 short questions. First, do you do the analysis online?
Yes, now I do it online.
Second, you mentioned twice the brain regions. So do you assign the features to brain regions? You mentioned medial prefrontal cortex somewhere in the middle.
Yes.
And you mentioned amygdala.
Yeah.
Do you have other brain regions representations going, as I understood, the sensor is somewhere in front?
Yeah.
So can you get to the midbrain reticular formation or posterior visual cortex?
Yeah. It's a little premature to answer that because real validation or gold standard comes from functional MRI. The problem is that the signal cleaning that is done on functional MRI, the EEG, because we have now electrodes in a huge magnetic field, so cardioballistic and other noises, the MRI noise itself is actually affecting the signal, so they actually kill the signal. Like when they do pre-processing and remove noise, they actually throw part of the baby with the water. So it's a little bit difficult to do that, but that's topic for future study, of course. Right now, what I can tell is that, you know, with different people, I can see the same region active in different people. I didn't mention the dogs too much, but the detection of the dog sniffing and detecting something is based on the same excitement as I have on humans. Actually, I'm using the same features on dogs that I use on humans.
Did you try smaller animals, experimental animals?
No.
And the third question, it
But
is
I'm
just
going to.
of curiosity. I noticed that you mentioned that these are all the same 120 features.
Yeah.
But I noticed that on some of the graphs, you have sequential readout of them going from the last.
Yeah, just technical issue. And some there are some number names. Yeah, the same exact features.
Hello.
Yes,
Thank you.
sure.
I have one question about the kind of performance of all these applications. For example, in the previous years, and you know the Kaggle site that hosts some machine learning competitions,
Yes,
and there was like few competitions about the neuroscience, and there was one about the prediction of epilepsy.
I know.
And the kind of the performance was like precision was about 80%, so it's kind of not like 99 or 95. And there was one about like to understand what
Yeah.
person is seeing. Is it like the
Yeah.
face or some blurry image? And the performance was like 70%. So it's not kind of. I'm just trying to understand. Is this really near future? Like we can get this in next year, or it's like in next 10 years?
Okay, so let me answer first about epilepsy. It's actually very complicated. When you read the papers, you get some papers talking about 95 to 99% performance in detecting epilepsy. Some papers talk about much, much lower performance. If you read carefully the paper, it turns out that epilepsy that is in the motor area of cortex, which is very close to the EEG electrodes, can be predicted very, very easily. Epilepsy that is deep inside, in the emotional part of the brain or closer to the brainstem, can predict it very, very badly. However, your Russian Dostoevsky described in his book, The Med, or how you would say it, he described his aura that he gets about 3 hours before an epileptic seizure, which obviously was close to the brainstem because he was feeling it as dry in the mouth, etc. So going through the vagus nerve and suggesting it was near the brainstem. So obviously one can see it, okay, or the vagus nerve, which would be the heart or the mouth, is interpreting the abnormal activity that is occurring in the brain. So one, it is possible to detect it, and two, I believe that this is the kind of way to approach it. I have to say that in detecting epilepsy, people have devised more sophisticated techniques for measuring correlation between neurons. Okay, all sorts of things coming from physics, but still, this is not the right way to do it. I believe that separating into different regions and looking at each region and noticing abnormal activity in that region is the right way to do it. I hope it's much less than 5 years.
So I'd like to remind everybody watching us online that you can ask a question on Twitter and using hashtag #YesScience. And we actually have one question like that. Could we influence the dream one is watching, like stopping nightmares?
Could we
influence the dream one is watching? So basically, if we can detect that person's having nightmare, can something be done to help him?
Okay, so we're going into the topic of brain stimulation. And as you know, this is now a big topic. So there's electric brain stimulation, either DC or AC, where you put electrodes on your brain and you in different regions and you stimulate. There is magnetic stimulation when you apply a certain magnetic field to a certain region in the brain and you stimulate it. And of course there's deep stimulation where you put an electrode inside, then you stimulate a very, very small region, but you know exactly what it is that you're stimulating. I believe in deep brain stimulation, because this tells you exactly what you need to do. This is very good now for Parkinson, for depression, for a lot of issues where you know kind of the region in the brain where this abnormality occurs. Those more global stimulations where people put electrodes and stimulate different regions of the brain, I'm a little afraid of that. There's not enough regulation there. There's not enough knowledge yet. I once put such a stimulator on my forehead for a while to try it, and for the next half of a day, the upper part of my visual region was totally dark. So I would not recommend anyone to do it. I think it's a little premature. There's not enough studies about it. However, this, when stimulation will become much more refined, when we shall learn more how to do it, then of course we can alter and we can increase, for example, increase the activity of certain region and increase that susceptibility to collect, to improve memory, etc., etc. Yes.
I have several questions. The first one is about the dolphin, and the question you answered right now about diagnostic and about stimulation.
Yeah.
You know that dolphins, they change frequency. They
Yeah.
change frequency and they can see their cancer, as you know, and they can kill the fish also
Yeah.
with another frequency.
I know.
So you say that it's another thing, but I think it's the same. It's the same. You see, when you make a diagnostic, you stimulate also. What do you think about that?
So I didn't talk too much about dolphins. This is a fascinating animal. I've been doing research for quite a while on dolphins. And there are various areas where dolphins swim with people because it turns out that whenever a person goes into the water, the dolphin can detect immediately abnormality. So dolphins, it has been proven that dolphins can detect a pregnant woman 2 weeks after beginning of pregnancy. And when a group of kids, it cannot predict pregnancy, I didn't say that, but at least detect. And when a group of kids, young kids, go into the water, immediately as they go with their head into the water, the dolphin can detect abnormality in the brain of one of the kids and would go and play with this kid. And this technique is now used to increase the self-esteem of that kid. And so they've tried different abnormalities. Dolphins can detect autism, can detect all sorts of brain abnormalities. So they really analyze our brain with their sonar. So, I didn't talk about it. This is an amazing animal, and I've learned a lot about it, okay? I have 5 patents out of dolphins, okay? So there's a lot of stuff that one can learn. We can talk about that later, okay?
But my question was, can you see the difference between frequency? How did you choose frequency? Because the dolphin, when they make a diagnostic, they cure also at the same time.
But it's a little, it's too complicated, okay? So the dolphin is using kind of a delta signal, okay? So it's a very, very sharp signal, which kind of in spectrum has infinite or as close to infinite band, okay? And this is sonar, whereas I studied the EEG of the actual brain activity. So the signals are very, very different, okay? And the techniques are different, so it's too complicated to get into those differences here. I'm happy to talk with you about it later.
So you think that your invention will be just fine for diagnostic, not for cure?
Well, not for cure, but for understanding the problem, for detecting the problem early, for releasing medications or releasing other stimulus to help the person. So of course it will help curing, okay? By determining that the level of glucose has gone down, I can tell the insulin pump to release insulin, okay? And then I kind of solve the problem. So the idea is to close the loop, either with neurofeedback or with the release, sophisticated release of medications to actually affect a person much better. If I detect abnormality developing in epilepsy and release a little bit of medication, I can tell if that abnormality goes down, and I can do it way before the epileptic seizure occurs. That's really where we want to go to.
Okay, and I understood. Thank you for your response. But I want to ask you the second question. Did your invention past clinical research?
This is now being devised in various aspects, in the anesthesia, in attention, in kids. So this is now being studied in various places.
And when are you going to introduce this invention to diagnostic?
So right now we concentrate on lifestyle because that's much faster. So neuromarketing is excited, monitoring people for kind of attention, etc. is exciting, doesn't require FDA regulation, it's much easier. We are starting with that and we shall get to the clinical results and FDA approval, etc., as we go along. We know that this is a much slower process. As soon as possible. I mean, this is now being commercialized. This is now being commercialized, okay? The dogs are kind of moving very fast, so it's really moving now. This is why I have started talking about it in the last year. I've been doing this research for a long time, but now it's ripe to start talking about it. And you know why you talk with people? Because you want to raise money. So, sure.
Thank you very much for the talk. I have a couple of questions. We could have seen on the graphs that measurements are taken just a couple of seconds from each other. Is this the maximum current time resolution for measurements?
I use a resolution of 1 second between measurements. I didn't see a reason to go further beyond that, maybe in the future.
Yeah. Also, you are now working with just 2 sensors.
Yeah.
And if the amount of sensors will be increased, is it possible to improve accuracy or time resolution? And how is it going up, exponentially or linearly or something like that?
I don't know. Namely, I mean, the point is, I'm very far from the ceiling of what one can do with 2 sensors. If I keep it to 2 sensors, 2 dry sensors on the forehead where no one has hair, it's much easier. You just put it and it starts working. If I have to go to other regions in the brain, first of all, there's hair, the dry sensors don't work, you have to use gel. It's a totally different story. It's much more obvious. It's not mobile. The point is to go mobile, to obtain compliance of subjects, you know, people who play games or people who just want to have a Fitbit on their hand and not something sophisticated. So it's too early to say. For research reasons, obviously, it's much smarter to apply a 256 electrode helmet and analyze it with these techniques. This is slowly happening.
Just about, we could use 2 sensors for mobile sensing and for medical research in the hospital, for example, use more sensors, or maybe not dry sensors, maybe wet sensors.
I mean, I try to explain the total different concept, okay? So when we use a lot of sensors now, we use kind of triangulation or what's called beamforming in sonar, where we try to kind of determine where the signal is coming from based on the different time that it arrives to different sensors. I'm using something totally different. Okay,
no,
I'm basing the technique based on the color or the timbre of the signal that's coming there, and therefore 1 sensor is enough. Okay. Now it's true that the signal coming from the back really decays when it comes to the front, and if I would put more sensors, I would see more information.
Yeah.
But for now, 1, it gives me enough work, and 2, there's still much more to do with 2 electrodes, and it's premature to jump before.
And the last question: are those 121 factors handpicked or automatically generated?
I couldn't handpick. That would take several lifetimes. No, it's all automatically generated. Okay, so everything, all that was picked was the mathematical constraints, the mathematical theory to generate them, and the data. And the rest is automatic. Okay. Here.
Good afternoon. Thank you for the report. And as a student myself, I was actually really concerned by your recent topic. I'm in constant monitoring human brain and using EEG while studying. And as far as I actually understood, it monitors the attention span of the student, and it actually more or less adapts studying course to the individual capacities of the student. But is there any practical proof that this constant brain monitoring somehow enhances the cognitive capacities of the student, or is it just a more convenient way to study without improving the average intellectual level?
The classical situation of an attention deficit student, they would say, the first 10 minutes of your talk, I followed everything, then I lost you, and I could not get back to the talk. So their attention span, the usual is kind of about an hour. Their attention span is about 10 minutes. After 10 minutes, they go out for about 10 minutes. But when they come back to a totally different part of the lecture, and they cannot kind of fulfill and go back. And so they're actually losing the next 40 minutes. If one would monitor the attention and see that these are the 10 minutes where the person is gone out, this is the time to revise, to play music, to do something else, and wait and see when concentration comes back in order to apply the more advanced, the new material, etc. This, now, as a teacher, it's very easy to see that the person is losing attention. We see that in the body language, we see that in the facial muscles, etc. The brain doesn't do that. So some people try with computer vision techniques, put a camera and analyze, the time of the dilation of the pupils, the eyes closing, etc. But one really wants to look into the brain.
So basically, you say that it actually only optimizes the studying by catching the moments when the student is more active, but is not beneficial for students' brain anyway.
Well, I didn't. I'll go a little further. Okay, some people learn from storytelling. Some people learn from animation. Some people learn from a movie that actually demonstrates things. Okay, every one of us is learning differently. By monitoring the attention, one can actually tell that this person prefers this kind of teaching and this person prefers that one. So we're going into individualized teaching, we're going into individualized time of introducing more sophisticated material. We can tell a person that a person forgot to take his medication, or we can say that the medication stopped working. We can really actually expand much more. Okay?
Thank you.
Nathan, thank you for coming and for this great introduction to this field of research. I've been watching to these pictures for some time now. I understand that
now you understand them, huh?
Almost. You have now 121 signal features you analyze, and maybe there will be more.
I'm working on 360 for the last half year, but I'm not publishing that.
360 signals features here,
yeah.
but they're quite picturesque. You show them, emotions go up, down, watching moves, but it all depends on how you sort them in this picture.
Of course.
So what do you show here? How do you sort it?
You know, in machine learning, you have to make assumptions about the data. If the assumption is correct, your model will be more describing the data. If the assumption is incorrect, the model should not work. Okay? If someone tells you that their model is always good, independently of the assumptions, something is wrong. Okay? So the assumption was that there is some order, that there's a conductor, and actually there's a symphony there, as opposed to every instrument playing by itself. Why? Because, we have a lot of literature suggesting that, okay? So I built that into the assumptions of finding those features, okay? You see, the features are time frequency features. The number of such features is infinite. And the question is how you devise the better ones from the worse ones. And we know from machine learning that when you have a model with potentially infinite number of parameters, the only way to solve that model or to find the correct parameters is by introducing a lot of constraints. And I've been writing many papers on imposing very innovative constraints on machine learning models to go out of the problem of having a huge number of parameters in a model with very little data, which is kind of what we have. So the temporal structure, the geographical structure was put into the constraints as part of building and finding features that are actually helping.
So the order of your signals
Yes.
on these pictures, is it
Yes.
frequencies of wavelets or geography on the... You're guessing about geography of the source of the signal?
None of that. It's some kind of snakes in a time-frequency domain, okay? And those snakes are representative of the color of the signal because they measure the higher harmonics, etc., okay? This number of such snakes is infinite, and choosing the right ones is really the whole thing. I did not get into the details how I do it because one, it's complicated, two, it's IP issues, etc. But this is the difficulty here.
Thank you. My question is about alternative way for getting data, such as single unit recording. Because of invasiveness, we can get much more accurate and localized data from the single neuron. And in your opinion, are there any perspective of using this technology for monitoring healthy people states?
That's a very good question, okay? So if we go with functional MRI, it tells us that regions that are about 1 millimeter cube are very, very indicative. The functional MRI divides the brain into 65,000 such voxels, and we can learn a lot about that, okay? If we go into single unit or even potential field, mean potential fields, we actually see a region much smaller of very few neurons. I believe that analyzing this forest should not be done in the leaves, should be done at the forest level, okay? So at the level of trees, which is a large combination of neurons, and at the level of even larger kind of forests, which is a distributed network of neurons. Looking at a single neuron, yes, there's a lot of research about single neurons, and we have grandmother cells, and we have monkeys that recognize their trainer. But when you really look at how the experiments were done, okay, it turns out that this monkey his life depends on this trainer. So every cell in his brain is actually excited when the trainer shows up because now we're going to go out for a walk, we'll have fun or we'll have some food, okay? If you really want to find that grandmother cell, that's very, very complicated. Okay, so some people say in UCLA, they take subjects that are coming to epileptic operations where they put electrodes in their brain, and for about a week or 2 weeks, those subjects become total guinea pigs for research. And the way that they find what these cells respond to, they say, these are features in the visual cortex, so they show them pictures. They've devised this way to show them thousands of pictures very, very fast until they find that, there's one neuron that responds to Halle Berry. You probably have seen that famous paper, okay? It doesn't respond to actresses that look like Halle Berry, only to Halle Berry. Nice, but you cannot really learn how the brain works from that. That's not so useful, okay? I mean, to continue, the signal itself, if I'm talking about the signal processing, the signal is much, much simpler at that level, and you don't need a sophisticated decomposition because there's activity of one neuron.
So we still get time for a few questions more, let's say 3 questions.
Thank you for the talk. And there is a question. You said that you use 1 second period for analyzing the signal to extract these 121 features. And what do you think is the approach can be changed so that the period could be shortened from 1 second to maybe half of a second or some kind of that? And what should be the sampling frequency for that, or can it be done using this approach?
So it's a topic for future research. I'm looking into it now. It's a little premature to talk about it. But these are all very good questions. I hope to be able to answer some of them in the near future.
Okay. Thank you.
I'm very curious about this amazing line of thoughts, as you call them, and I'm curious why they have like two separate line of thoughts which are negatively correlated. Have you idea why it is so?
I think Arkady mentioned it. Okay, so you order the data, and then you try to find a certain ordering.
Yeah.
And as you know, this is an NP incomplete issue, so you don't always land at the global minimum until you land at a certain minimum. The truth is I have better minima now. However, I've been using this ordering of the features for such a long time. I don't want to change it now because then people will be nervous. So it's true that there are things above and below, and sometimes they are totally reflective of one another, like a mirror, sometimes not. So it's kind of very interesting. Obviously, there may be a better ordering, but this is good enough.
And the second question is, if you have, say, 100 people who are watching the same movie, and what is your prediction? How similar the line of thoughts should be, or you should find some clusters, or what is your prediction?
So the CBS study was exactly that. Okay, a group of people watching the movie, in groups of people watching it together, but basically I was synchronized, so I get all the people watching the movie exactly at the same time. And the determining engagement was very, very simple. Simple clustering that told me that a large number of people in the group were found in the same cluster. If it was found in the same cluster of brain states, I could only predict that it had to do with the stimulus. When they were not engaged, everyone was in their own brain state, and then, I determined this is less engagement. So it became very, very simple, okay? Based on the clusters that one could devise from this vector of 121 features. So the whole task was clustering in this high-dimensional space.
Thank you. I wanted to ask a question about sonar beds. You showed a slide where there were bandwidths of sonar beds, and I wanted to ask, how did you manage to measure with these curves? It's very hard, I think.
Okay, very interesting questions. So there are about 800 species of bats. The smallest one is about this size. The largest one is like an eagle. So that's like a huge, very sophisticated family of animals. Not all of them use the same sonar techniques, by the way. Okay? Now, this is at the lab of Professor James Simmons at Brown. I'm not collecting data, I'm just analyzing data. Other people collect data. So he has a very sophisticated lab with an acoustically clean room. There's a bat that sits on a plate, and he's giving a target on one side and a target on the other side. On one side, the target is moving. On the other side, the target is not moving. And the bat is supposed to go to the moving target, okay? And if the bat goes to the right target, it would get food, so that's the training that is being done. There's actually no target there. So the bat is emitting a signal. He collects the signal he records the signal, then analyzes the signal, converts the signal into a response, kind of simulates a target, simulates a moving target, and so there's a total control on the signal that the bat is receiving. The level of signal to noise, removing some bands, increasing other bands, etc. This is like becoming a black box for an engineer to analyze, okay? And then you can really quantify the result of the bat, okay? So this is now, I did it with James Simmons. There are several places, Konishi in Stanford and at Maryland. there are several places that people do this kind of experiments. So from behavioral experiments with manipulating the signal, one can learn a lot about how the brain works.
Okay, thank you.
Sure.